AB, here we go, 6.4. Next pages. All right, a little bit of review. So net area is just the definite integral. On the calculator, you're just going to put math 9, Fn to f of x, and then the lower bound and the upper bound. If it's total area, you just want to put absolute value around the function x, a, b. Okay, and then absolute value is just, right here. If you want to just do math, go over 1 to num, hit absolute value. And then like absolute value of -3, we'll get 3. Okay, so that's math. Go over to num, and then it's option 1. Okay, so we're going to look at this concept of area a little differently, all right, as a new kind of function. So we're going to look at area as this new function, kind of in general. And then we're bringing this in because this type of question is usually on the AP exam. So, all right. So this is area here, a of x, is the integral from 0 to any x. Like if I wanted to plug numbers into a function like f of x, a of x, we plug it, you'd plug the x in as the upper bound. Okay, so that's what we're going to do here. And then this FT, really important right now. Okay, really important. If you then look at a prime of x from FTC number 1, okay, a prime of x was going to be equal to this f of t, right? If you took the derivative here, you're going to get this f of t. Well, you would get x in there. But not really that worried about the variables. But just imagine if you differentiate this integral, then this is just f of t. All right, f of x here. Okay, so what they've given us here is the graph of f of t. That really should probably be listed. And then here they want the graph of f of x, or a of x, sorry. So what is it? It's really important to note that this is, if f of t, which is behind the integral, when you have a new function, okay, when you have this like new function, I don't really, the answer here is kind of a weird thing for me, but you have this new function, and it's going to represent accumulating area between this function f and the x-axis. All right, so this is f(t), that we're going to accumulate this area. All right, so just note when you have a function and it's written in terms of an integral, then the piece that's behind the integral is the derivative of kind of the master function here. This is the same thing as a prime of t, and we'll use information about the derivative then to graph a of t. We're going to do that page after page here. Okay, but we start slow and do the integral, so we're going to start accumulating from 0. So let's go 0 to 0. Well, that's just 0. So I don't have a function to integrate here, and so that might happen on the AP exam, that you've got some situation that you're asked to integrate in with an integral of a function, and you don't have an actual equation, so you got to kind of have to think about what it all means. So that's what we're doing here. All right, and then if it goes from 0 to 1, now here's an example where we can, we can integrate this thing even though it's not continuous overall. But since I can bring this down and lock in this area, I can do this. So a of 1, if I plug in 1, 1 becomes the upper bound. That's asking me to do the area from 0 to 1 of f of t. This is f of t. Okay. which is going to be the equivalent of a prime. All right, so this is 1 by 2. That's just 2. Okay, so let's go to 2. Now, so then what is the area of A2? So what's the area under the curve of 0 to 2 of this f of t situation? Well, you know, I could just use what my previous, hence the word accumulating, my previous answer here, obviously you could use your previous answer of 0, but previous answer of 2, and then add in this new right here. This is a 1 by 1 is 1, so this is 3. All right? And so notice I'm basically plotting points here for a of x. If I were doing a t-table, if I plug 0 in here, I get 0. When I plugged 1 in, I got 2. When I plugged 2 in, I got 3. Okay? And so the next one, a of 3, would be what we got here. Okay, so the 2 plus the 1, the 3, and then let's go from 2 to 3. Well, from 2 to 3, I'm below, so this rectangle has to grab the x-axis this way. And so that's a 1 by 1, but negative. So this is 2, 1, negative 1. Okay, so we have to add in a negative 1. So now the accumulating area is 2. And this is net area. Okay, so it's net area. But we're kind of thinking of it as point plotting now. And then last but not least, we can accumulate 2 and now go from 3 to 4. And 3 to 4, we're just flat. So the point there is just 4, 2. So that's what we're doing there. So a of 1, you plug in 1, you know, for x, where does it go? That's the upper bound. And then we look at this graph of f of t. Okay. All right, and so then it doesn't really say here to graph it, but let's graph a of x. All right, so a of x has a point 0, 0, and 1, 2, and 2, 3, and 3, 2, and 4, 2. Okay, and so those are those points generated, and now the derivative information will tell me what to do. Well, this first piece up here shows me that I have a slope of 2. And my labeling here is kind of, that was the dimensions of the rectangle. This is the point 2. That was for a 1 by 2 rectangle. So this, the graph of the derivative, means a slope of 2. Okay, which makes sense. That had a slope of 2. This has a slope of 1. Makes sense by the points. Right here, slope of negative 1. Points are consistent, and this is 0. And those points, the dot to dot, that's consistent with the graph of that derivative. So that's a little bit of an intro to what we're doing long term. Okay, moving on. So this is the most confusing part about this next piece, is that I'm going to constantly have to flip back from page to page. But okay, so here we go. Continuous function f of t defined by the linear segments that connect the points. Okay, so f of t is here, 0, 0, 2, negative 4, 4, 0, 5, 4, 7, 4, and 8, 0. 7, 8, 0. Okay, so points are here, so I'm just going to kind of keep this clean so we can look at it. Sketch the graph of f of t. So this is f of t. Now look at this definition. G of t is the area under the curve of f of t. So if you took a derivative, you can see that this is also the graph of g prime of t, or actually x. Okay. All right. So find the following. So estimate, these are all clean lines, so I don't think we need to estimate. We can find these. So G of 0. So 0 is going in, upper bound. Okay. Go from 0 to 0. G of 0 is equal to 0. Okay, so this is the derivative. Now these are points on the master function. I'm going to grab hold of these for ease of use later. Okay, G of 2. Well, the integral of 0 to 2, of this situation, let's go to 2. So that's 1/2 2 by 4. 1/2 of 2 by 4 and negative. Okay, let's do G of 4. All right, so I could accumulate, or I'm going to pattern, but since they're both the same signed area, they're both negative, you could just start from fresh and go from 0 to 4 here and do this. 1, 2, 3, 4 by 1, 2, 3, 4, right? And get 1/2 of 16, get negative 8 here. But I'm going to use the accumulation piece. And I'm going to say, well, let's take the previous one and add on just then from 2 to 4. I'm not writing all the integrals out here because of a lack of space. But so I've taken care of this one, right? That's negative 4. So now let's add this one on. Okay, which is equal to, so as predicted, negative 8. So let's add these back. 2 is at negative 4 on G, 4 is at negative 8. All right, again, you could have just done the whole thing as 1, 2, 3, 4, 1, 2, 3, 4, half of 16 in the negative, negative 8. So we're there. But now, in accumulating, we want to make sure we add in this piece when we cruise on over to G of 6. Okay, so now we're here. So I've got to add in this piece. Okay, and so G of 6 is going to take that negative 8, and it's going to add in this trapezoid. So 1/2, base 1 is 1, base 2 is 2, that's 3, and 1, 2, 3, 4. All right, so G of 6 then, just point plotting here, this is just calculus point plotting, is negative 2. So at 6, I'm at negative 2. And last but not least, G of 8. So I'm going to pick up that negative 2 and just go from that stopping point to here. And this looks pretty symmetrical, 1 by 2 by 4. So this is also going to be the same trapezoidal shape, 6. So that was 6, and that's 6. So this overall accumulation is at 4. All right. So basically, if they'd asked you to go from, all the way over 0 to 8, and the net result is we're just kind of modeled by the accumulation Bach process. Okay, so lots of questions about this on the next page. Find the largest open interval on which G is increasing. Explain. Okay, so we're gonna look at this. So let's graph G of x. Let's graph G of x. So 0, 0, I'm just grabbing these points. I'm grabbing 0, 0, 2, negative 4, 4, negative 8, and 6, negative 2. Oh, and I didn't add, sorry, 8 and 4. Need one more. 8 and 4. Okay? So we are going to use those. Like I said, it's the flipping is the worst part of this. So there's 0, 0. At 2, we're at negative 4. And at 4, we were at negative 8. Okay, and then at 6 we are back at -2, or we're at 6, we're at 1, 2, 3, 4, 5, 6, we're at -2. And then at 8 we're up at 4. Okay, so those are the points. All right, where did I get those points? That was point plotting on a point plotting on a function that involved an integral. So just plugging 0 and that being your upper bound, 2 your upper bound, 4 your upper bound, but accumulating as we go. And just writing each one of those integrals out would be kind of a lot, but hopefully that makes sense. So there's that. And then remember, I still have these points here. I still have this graph here. I still have this graph here of f of t to help me figure this out. Okay. So this tells me, this is information about the derivative. So this is negative. Okay, this is negative. So it tells me I'm decreasing until 4. Okay, well, by point plotting, yes, we are decreasing until 4. So that's great. Everything's copacetic here. And so, but let's talk about concavity. So this is going to be downhill, concave down, and then concave up until we get to 4. So let's do that. So something like that. Okay. And then this tells me, flip. This tells me I continue to be concave up, but now I'm increasing. So this is going to end up being a local, right? That's 0 on the first derivative, and we went from negative to positive. That's going to be a local min. So we continue to be concave up because we're uphill, but we went from increasing. We went from decreasing below the x-axis to increasing. So let's model that until we get to 1, 2, 3, 4, 5. No, it should have been, yeah, until we get to 5. Okay? So I think this is my point. This is my point 6, -2. Okay, so I want to kind of think about what happens at 5. I'm going to push this over. So it looks 1, 2, 3, 4, 5, 6. Okay. All right, so we're going to go like this. All right, but at 5, so somewhere about 5 here. So it'll be increasing and concave up. But at 5, we have no concavity. So from 5 to 7, there's no concavity, and then we go concave down. We stay increasing because we're above, but from 5 to 7, we have no concavity. So we're linear until we get to 7, and then we're concave down. So 7, we'll put 7 on there too. Linear till 7, and then sort of concave down the best I can do there. It's going to be linear in here, no concavity from there. Funky little graph. Wow, that's a lot to process, okay? All right. So this is g of x. There you go. And so we can answer our questions from either g of x here, or we can answer them from g prime of x, which is f of t on the previous page. Find the largest open interval on which g of x is increasing. Well, I like open because I have to think about it. 4 to 8. As g of x is increasing, or f of t is positive. All right. And then where are we decreasing? Well, 0 to 4, it says for open, so we're going to go 0 to 4, as g of x is decreasing, or f of t is negative, meaning below the x-axis. Extrema would definitely be here at x equal to 4, as, let's just say f of t was equal to 0 and, switched from negative to positive. And this is also an absolute. Absolute. Min. Local min. It's also an absolute min as f of t continues to be positive from 4 to 8. So, just a little fun fact right there. Okay, it's also an absolute because this bottoms out here and this f of t stays, or g of x stays increasing and f of t stays positive that whole way. Okay, suppose, and we'll stop here. Suppose y equals f of t represents the velocity of a particle. What then does we've already answered this question, a lot here. What does f of t, y equals f of t's velocity, what does this represent? Well, you've integrated up to position. So, but it's accumulating position. So this is more of an accumulating thought. And accumulating position still just means slash net position, which is, as always, displacement. When is the particle moving in a positive direction? Well, same as when it's increasing. And this doesn't say anything about, so I'm going to use when we're increasing, I'm going to use open intervals here, 4 to 8, but I'm going to close the endpoints now. Okay? And again, that's because, g of t, or g of x we can see here, but with calculus we'd say because the derivative is positive. Backwards is 0 to 4 because the derivative was negative. Okay, and that's just our graph over here once again. Below, and above. Easy. T equal 3, what are the particles' velocity and acceleration position? Okay. So, wow, thank you for asking me about a point that is not on our T table. So, but actually, that's okay. It'll help us figure out what to do here. Okay, so position. So I need to do, we've already just discussed that v of t is velocity, so g of x is position. All right, so g of 3. All right, well, g of 3 is going to be the area under the curve from 0 to 3 of f of t dt. So let's check it out. 0 to 3. Let's refresh my space here. So it's from 0 to 3. Okay, well, I don't know what to do with that weird shape. So we're going to just do this. Okay, so this was 2 by 4. Okay, 8, and then divided by 2. So this was our negative 4. And then this, as a trapezoid, is 1, 2, 3. 1, 2, 3, no, 4. 4, 2, that's 6. And then 6 by 1 is, of course, 6 divided by 2 is negative 3. All right, so g of 3 is negative 7. All right, so let's go back over here. G of 3 is negative 7. All right, that's your position. Okay, its velocity then is going to be f of 3. Okay, so let's go to our f graph, which is here. And where am I at 3? 1, 2, 3. Where am I? Well, I'm at negative 2. Okay, so, you want to be careful if you have to do some algebra, please do. But this is 1, 2, 1, 2, 3, 4. So you can see your slope is 1, 2, 3, 4, 1, 2, slope of 2, so 1, 2, and over 1. So it definitely lands you at negative 2. So this is just f of 3 is negative 2. And then so acceleration would be f prime of 3, which is the slope at 3. And that slope of 3, we already talked about that. That slope of 3, flip, flip, flip. This slope here is, that little segment has a slope of 2. All right. So at t equal to 3 is the particle speeding up or slowing down. So velocity is negative, acceleration is positive. So we are slowing down. Velocity and acceleration have different signs. Okay, if we assume the particle is at the origin and when t equal to 0, approximate when does the particle pass through the origin? Again, well, I guess I'm going to use IVT here. That's really all I know to do. So I'm guaranteed to pass through the origin sometime right here. Between 6 and 8? Because that's my graph of G, so let's see what it looks like over here. So this is 6 and 8. So yeah, somewhere between here it's got to pass through the origin. Okay, so by IVT it's continuous, all that good stuff. Seconds, I don't know what we're doing. What is the total distance covered by the particle when t equals 8? Okay, gosh, I've got this all sideways. All right, so let's go pick up all of our integrals. Total distance. Okay, so now I want you to think partitions now. I want you to think partition, not accumulate. So let's go look at all of our partitions. Okay, let's look at all of our partitions. Okay, so our first one was 0. Our next one was negative 4, so we need that to be positive 4. Our next one was g of 4 was negative 8. I just wrote negative 8 without an equal sign. Negative 8, so there, and then g of 6 was negative 2, and then 4. So I'm just going to take all of these and add those guys up. Wait, no, that's not what I want to do. I want to add all the areas up. Sorry, add all the areas up, not the points. My bad. So let's go back here and see what all these were. Those would be the nets. Sorry. So to 2, we were at 4, so I want to think about that as 4. And then this was 4. And then we split these, right, 6 and 6. Or you could just do a triangle 1, 2, 3, 4, 1, 2, 3, 4, 16, 8, total distance, negative 8, make it positive. And then you could just do a nice trapezoid 1, 2, 3, 4, 1, 2, 3, 4, 1, 2. Okay, so those bases are your 6, 1, 2, 3, 4. That's 24 divided by 2 is 12. Yeah, so this is going to be the representation of total distance. Sorry, not this. My bad. I was kind of spacing out there for a minute. All right, so total distance is just that 4 plus 4 plus 6 plus 6, and that is 20. And that would look like, you would just be flipping up that piece there, and this was that weird trapezoid. Well, it's not a weird trapezoid, it's a normal trapezoid. But so this would be that 8 and that 12. It was split of 4, went to 8, x, y. So if you were to do that, more beautifully, you would just kind of model this graph and just flip that up. Okay, Okay, my goodness, I'm tired. All right, next one. This is easy. Use definite integrals to represent the total distance traveled, 0 to 8. And we're just going to throw that in absolute values, d. Okay, so that's a lot to take in, a lot of just notation and nuances to process. So let's look at what's next. And I'm gonna stop, but I just want to kind of do the end of. I'll just save this for the end. So here's one more piece to 6.4 part 2. So I'll call this last page, but we'll start it right here. All right, guys. Thanks for tuning in, those of you who did, and we'll see you in class. All right, signing off.